pieces of it going that we can, and I may be asking some of you to sign a letter soon to help promote its continuation with our leadership. Just listing the 3 goals here of Focal Area 3, I think what I'm going to talk about today with our turbidity work touches on all of them to some degree or another. We established a sensor array back in 2011 on this boulder just upstream from the Rio Cacos gauge. Photos, my colleague on the lower right there, Gianfranco Saraceno, who's really been instrumental in keeping these sensors running.
Hey Jamie, I don't see the slides in any kind of expanded view. Can you go to a different screen to share? We just see the slide deck in the thumbnail version.
Because I have it in presentation mode.
Does anybody else have the same problem?
Yep, I see the same thing. I think maybe you're using 2 monitors and it's not sharing the right monitor?
No, just one monitor.
I think what happens in presentation mode is that it does just what it's doing, that we don't see the presentation you do. And so you want to, or it's like a different, there's some trick for a Mac that makes it work right. I don't know what it is.
So what do you see now? Do you see the slide in, I'm in like notes mode, I see it.
Same thing.
So you've seen all my slides, like the whole deck?
Yeah.
So none of these things change it for you?
Nope.
I'm changing it around, huh? Anyone? I've never had this issue before.
Well, so one thing you could do is to not use the slide mode. I mean, just go to your, like, you know, like when you're editing the slide, whatever that looks like.
Yeah, well, I did that, and you.
Oh.
I'm in that mode now.
Huh.
Maybe try stop sharing and start sharing again.
Yeah.
Yeah, exactly. Could
the other thing is I guess I could save it as a PDF and maybe go through it that way. But, all right, so stop showing screen. Okay, you don't see it now?
Right.
Right.
Now you do see it?
Yeah.
Now it's
try presentation again, just for fun. So beautiful, beautiful.
Oh, it works now? Good.
Yep.
Perfect. Okay. So yeah, I think I was on this slide just showing Gianfranco in the lower right.
And then if you, I do want to protect the Earth, but maybe you can close the, because we're missing the.
You see my panel here too?
Yeah.
Oh.
Yeah, that's good. There we go. Got it.
You protect the Earth later on. Okay.
Yeah.
Okay. So I have some notes here I meant to delete, but so here's some of our long-term record, about 2 years worth of data from 2014 through part of 2016. And here I have a discharge on the top and turbidity on the bottom. So, you know, these peaks line up very closely, as you might imagine. But I'll get back to some of those longer-term data, but I want to talk especially about these huge events we had earlier this week. There were about, well, as you can see here, about 10 inches of rain. They came in 2 blasts on Easter Sunday and the day after. And Angel, are you on the line? Angel was going, oh, good. Yeah, so Angel got there in between the storms, collected the first one, and then got back to collect the samples from the second one. We finally got our ISCO set up and got samples from these storms with some problems, but we got fairly good coverage. So here are the hydrographs. I'm sorry, this is the turbidity. I got these out of order. So even though the first storm was a little smaller, the turbidity spike was a little higher. And these are about the highest turbidities we've seen in the whole period of record. And just at the bottom there, the flow rate, that should be 33 millimeters per hour. That is the runoff now over an inch, about an inch and a third per hour of runoff. So it's just incredibly high flow rates, as Luquillo is famous for. And this is an old photo, but just to give you an idea, the flow, the stage height was about a foot higher than this. And the flow is completely covering the wall, the weir wall. Here's our fluorescent dissolved organic matter, and you see these dips. Oops. The dips, like in the middle of the storms, are not real. Those are caused by the interference from turbidity, and I'll talk a little bit about the corrections we do on those. Conductance, Luquillo is also famous for tremendous dilution. However, if you look at the April 19th, that big vertical rise was when the sensor got unburied from sand. So we're not sure how much of this particular record to believe. It's not unprecedented to have the conductivity drop from 50 down to about 4 as the plot shows, but we're not sure when the sand began to affect it. And we usually don't have this problem with conductance, but this was almost the mother of all storms. So I got these labels mixed up too. This is the actual stage. So if you're familiar at all there, the top of the wing wall is about 4.5 feet, and this reached almost 6 feet. So incredible amount of water. So here's the turbidity plotted over top of the discharge I split the storms up into the two different storms. So this is just the first one. And we often see the turbidity not really preceding the peak discharge by very much, but in this case it did. Crazy units here, but it's by about 30 to 45 minutes. It's just a 15-minute time step, so somewhere in that range. And the second storm as well, the turbidity preceded the discharge by a little bit. And then when you look at the hysteresis, so that produces a clockwise hysteresis, and you have pretty pronounced loops for both storms, and they look very similar, two storms. Now looking back at some of the older data, I just quickly pulled out a few different storms, and here's what we often see where the turbidity, so here we have the flow, it's actually stage height, but and that's in blue, and the turbidity is in the orange color. And their peaks are fairly coincident in this one. And here's one where they're also fairly coincident, but different sort of responses to different phases of the storm. And here's a series of storms where we just get these different types of behavior for different storms. This is kind of an unusual one where the turbidity sort of hangs out at a high value on the recession limit of the storm. But, and I'm diving into this analysis in preparation for a poster I'm going to give at the all hands meeting on these data, but I've got to think that the variation in response we see can tell us something about the source of the turbidity of the particles. And this is a little out of order too, but the correct one way we use the turbidity, I mean, we're trying to use it to get at particulate carbon because we're trying to do complete carbon budget on the stream, and it looks like it's going to be a pretty good proxy. But we're also trying to get DOC, and we have a fluorescence sensor in the water that is a proxy for DOC, but it's highly affected by turbidity, so we have to correct for it. So the blue line here is the raw value, and the green line is after our turbidity correction. And I have a few more slides on that later on. I meant to put this with them, but I might get into that if there's time. Here's a picture of the sensor with the turbidity on the left and the FDOM on the right. And you can see the brush at the bottom of the photo that swings around and wipes both of them off before every measurement, every 15 minutes. Now, some photos of this event. So this is looking, we have our backs to the stream gauge. We're looking upstream towards our sensor array to attach to that boulder. And I should point out that Bill's team also has a sensor array there on the array to the left, which was installed about a year ago. So we have complementary data that we need to sit down and look over at some point. But the sand in the foreground, I have a better shot of it coming up. It's, well, here's what it looks like. Just a grab out of the river from that event. And if those of you who've been up there, it's often like walking on beach sand in that channel, but not right now. We had a lot of deposition of very coarse sand. And you're probably familiar with this view, although you're usually looking at boulders that we walk out on to view upstream and take samples, completely covered with sand. I've never seen these rocks covered like this. I'm sure Bill has, but
not to this extent. It's remarkable looking. I've never seen it like that.
It's pretty wild. Oh, and that's the wall on the left. That's, you know, where the flow was, again, about 1.5 feet or half a meter higher than that wall. So the person in that photo would have been underwater. And that's what it looked like after the deposition. At our staff gauge, now typical base flow level is about 1.1 feet. And our ISCO intake was at about 1.2 feet or 1.3 before the first event, and that's why we only got 3 samples from that event. So Angel raised it up for the second event and was very successful in capturing that event, although in that second event the challenge was that the particles were so big that the line clogged from particles, and we missed some of the samples during the highest turbidities. But there you can see the line after it's been raised up to about the 1.9 foot level. And so here's the hydrograph on that second larger storm, showing the sample coverage. So this is Angel's nice hand-drawn plot on the USGS plot, where the hand-drawn samples are shown and the stage values. And where the open circles are samples that the ISCO tried to take but didn't get any sample. And if you look at those two at 4.25 and 4.83, that's about when we were getting our peak turbidity. So the line was just couldn't handle all that sediment. But we still got fairly good coverage, and you know, a couple there on the falling limb as well before we ran out of bottles. We weren't geared up for quite this big a storm to get the whole hydrograph. And that's what one of the samples looks like. This is one near the highest turbidity again that we did manage to get, although we have it triggered to get 2 bottles for each trigger, and it only managed to get 1. But we'll run with it. And just to show another challenge with the sampling is, so on both of these photos, the pairs of bottles are from the same trigger. And you can see that, so these are basically at the same point in time, about a couple minutes apart. So they should have the same amount of sediment in them, and they clearly do not. So there was not completely representative sampling during these really high turbidity stages. So with these two, we're going with the assumption that the one with the more turbidity is probably more representative, and with the lower turbidity or the lower amount of particles have probably got clogged at some point. Oop, going the wrong way here. Yeah, so we're getting these samples into the lab, and we'll see how we did in terms of how the relation between turbidity and TSS worked out. So that's about all I had on that storm and a little bit on our long-term data. I just have a few slides. I guess that didn't take too long, did it? I can go another couple of minutes just showing how we're using the turbidity to correct our FDOM.
Sure,
Okay
go ahead. Yeah, go ahead.
Yeah. So, the turbidity interferes with the particles, I mean with the FDOM measurement, and this plot shows the fraction of light that actually makes it through. So as the turbidity goes up, turbidity on the x-axis, we're extinguishing more and more of the signal just because the light does not see through the particles. And if the blue dots show a fit using the only published correction value, which is also by John Franco's group in Sacramento, USGS, but our data are the I'm sorry, yeah. So the red are the downing data based on a laboratory experiments, and the blue data are the data that we collected at ICACOS from a filtered and unfiltered experiment. And you see that after you get above a turbidity of about 300, our data diverged from the downing correction. So in other words, if we applied the downing correction to our data, we would be overestimating the FDOM because it would be overcorrecting. We'd be assuming, like say up at 600, that we're only seeing about 10% of the light, and we're actually seeing 20%. So something about this character of the sediment at ICACOS lets more light transmit than in the experiments that Downing did. So we developed this local correction based on our filtered and unfiltered test, and we now use that to apply to our data, and we get a better correction. And just kind of summarizing that in a plot, if we looked at the uncorrected values on the left side there and compare that to our filtered values, which we take as truth, and the size of these points are proportional to the turbidity. So the points all lie to the left of the one-to-one line, showing that we're underestimating because we're losing light to the turbidity. The second plot shows when we apply that published Downing correction, and shows that we're overestimating at the highest turbidities, the largest circles, because of the different sediment character. But when we apply our local correction on the rightmost plot, we see that we're doing very, very well. And just a couple more showing pretty much the same thing in that bottom plot. The filtered value is the blue. When we use our site-specific correction in the red, we come pretty close to that. If we had used the Downing, we would have overestimated by quite a bit. And the dotted line is the raw value. So definitely need to do some correction. And the reason maybe this published value doesn't fit our data so well, this shows the percent fines in that laboratory sediment that they used in the Downing experiment is labeled ESL. It's up at 80-some% fines. It's a horizontal line across. And you see that might be good for, these are data from a lot of major rivers in the US, and we seem to hit that composition seems to hit the median pretty well. But just taking 2 grab samples from the bank and bed of the ICACOS River, those are the lines down at the bottom. So obviously much coarser sediment, and that indicates why the Downing correction probably was not doing very well for us. So ICACOS really did need this localized correction, but maybe a lot of other sites could rely on that published Downing correction. And again, this just compares the sediment that the Downing study used, the Elliott Silt Loam in blue, with those 2 samples we got from the Icacos, the size distribution is quite different. And that's what I had.
Great, thank you,
So-
Jamie. Just open it up for questions.
Yeah, Jamie, this is Doug.
Yeah.
I'm very excited about this, as you can imagine. So, I mean, I know that you always see hysteresis, but going back to that, what was the difference for the same discharge? Like, were they up to like a factor of 10?
For these two storms?
Yeah. Yeah.
No, the discharges?
No, I mean for the same discharge, how large was the concentration difference? What was the biggest difference between, say, rising and falling limb?
Oh, and this, yeah.
Yeah.
Yeah, factor 3 about.
Okay.
Well,
Yeah.
I mean, if you just draw a vertical line through the center of the plot.
Right. Right. And so when you presented the particle size distributions, those were just from the bed and the bank of static grains after the flow, right?
Well, well, yeah, I mean, this was
Mm,
just some random time that Angel went out and got sediment. It wasn't in response to any particular event.
right.
But
So-
obviously, looking at, the photos from this week, the distribution is not static, because it can go from beach sand to the really coarse stuff Angel was holding.
Right. So in terms of have you looked at grain size analysis on the ISCO samples through the flood to see how that how that distribution evolves?
No. We'd love to do that, and the way we're actually going to get the TSS concentrations on these is we're decanting off the water and then evaporating the rest, because we're just not going to try to filter this stuff. So we would have a lot of material available to do the grain size analysis.
Right. Because this is this is of course one of the things that we're interested in doing. Of course, if Hervé can get some real-time measurements of grain size distribution, that's cool. But it's always the issue that we have these huge variations in concentration, which presumably are, as you pointed out, are probably related to changes in source and type and everything else, but we rarely have data on the grain size.
Mm-hmm.
It would be wonderful to have information on the evolution of grain size through this flood, because of course some of the evolution of grain size will be related to the flow strength, but that part we can kind of understand and subtract out, right? And of course the hysteresis that you see there is the part that can't be explained by the strength of the flow. And if your idea is correct, we have the sense that sediment is switching sources or something like that throughout the flow. We should see a signature of that somehow, presumably in the size and nature of the particles that are there. And of course, ultimately, like, I'm interested in going all the way to, like, looking at the aggregates and all of that to understand the relationship between hillside sediments and the river. But a good first step would just be doing a grain size analysis on the complete sample, every sample that you can during a flood.
Yeah, I agree. I think it would be amazing data to have and give us a good idea on source when we compare it to the grain size distribution of the different potential sources.
Mm-hmm. Yeah. So you're gonna dry this stuff out, and you'll have the total amount. And then what are you gonna do with the sample?
Well, we do need to get send some of it to a lab for particulate carbon analysis. But if we can kind of split it out and get just a representative portion grain size wise, the rest would be sent to you, Doug, to do the grain size analysis.
Yeah, how are you guys doing it?
Well, this was done by John Franco Saraceno in the Sacramento USGS lab, and he actually did it with a list.
Yep.
Yeah. So this done in solution.
Right.
The laser technique.
Yeah. Cool. It occurred to me that, I mean, yeah, so the samples you were showing actually now have such a size range. Some of them are probably too big for the laser diffraction.
Yeah.
So we have a laser diffraction, a list type thing, and we also have the cam sizer, which goes up to like a centimeter. And so we can actually, we could sieve it if we have to and split it up and then run the two and add them back together.
Yeah.
But I would also be interested in looking at some of the grains under a microscope. So yeah, actually, we'd be pretty happy to receive them.
Okay.
Yeah, and it's not like a huge amount, right? I mean, you're looking at these. What do you have, like a dozen samples or something?
We probably have about 6 from this storm that
Right.
that we're going to evaporate that way.
Right.
The initial rising and late falling samples don't have that kind of grain size, large grain size. So
right.
it's a little difficult to send you, but
right.
That'll probably end up on a filter.
Okay.
Yeah, we can talk offline and make arrangements on that.
Yeah, good.
Awesome.
Yeah, very, very interesting. Very cool stuff. And,
I would just add one thing to Doug's comment about the flow, and that is that the rain intensity does seem to have a big impact on the turbidity, the strength of the turbidity. Kathryn has some great data. I don't think she's going to show today, but on one of our storms that she sampled that wasn't the highest rainfall, it was the most intense rainfall, and that caused a big slug of turbidity. So that's just another factor that we need to consider when interpreting these turbidity patterns over storms.
But we should have nitrate data during that storm as well, and also DO, so that'll be interesting and the Visalas likely working. We can't be certain until we look at the data, or we can't ever be certain about the Visalas. But in any case, yeah, so we should have a really pretty complete picture of the storm and a bit of data on the Salvador as well. I have heard that our sensors made it through the storm, so that's good.
Yeah, it's amazing that they can withstand flows like that. They've all had pretty good luck.
Okay, any other questions for Jamie? This is truly a hot moment that we captured here, so it's pretty cool. It's remarkable that, and I have to say I'm most impressed. Well, I'm impressed by a lot of it, but the big chunks on the bed are remarkable. I've seen those chunks down 1.5 meters underneath the surface while augering for wells. Way back when in the 80s when I put the Conco's well field in, there were chunks just like that, and they are very rarely seen otherwise in the stream channel. And to have all that sand moved around, it's like I wonder what the rest of the channel did too.
Yeah. So where do they go? Do they just get covered over by finer sand? Does another event come along and take them away? They just keep getting covered over. We should be grading like crazy.
Yeah.
At some point they get scoured out. What kind of events are those?
Yeah, I mean, maybe it's worth doing a grain size survey, you know, we have that those pebble, you know, the pebble count things where you get the D50. We have one of those on hand. Carla knows how to use it. Maybe we should do a grain size survey and just watch and see how fast it takes for whatever's on the stream bed to start to, you know, go back to the sand that we know it was. And we may have some initials also using that approach from January, February. I'll check on that. But clearly we could watch the progression over time from now forward. Wow.
Yeah,
Okay.
you know, looking at those, when you figure they're dumped like that on the bed when the flow receded, even those chunks could well have been suspended.
I would assume that they were. I mean, they. Yeah. I think. And was the whole sensor array area, Jamie? Was it all buried in sand, but is it now flushed out, or?
Angel, can you speak to that? I don't think there was any deposition there, was there?
No, in fact, all the old sand deposits were washed out. So the cross section at the sensor side is deeper now.
It was already kind of deep.
Although when we were there in January, it was the shallowest I'd ever seen it. So there had been some deposition.
Yeah.
Definitely.
No, that's clearly, around that bend, the sand was clearly quite variable, and throughout the channel. And so this is a challenge that going forward is to, I haven't thought about it quite this way, but understanding sediment and the sourcing of sediment across the weir, you know, maybe we should be looking more closely and systematically at the stream bed itself in anticipation of these big events, and you know, have some sort of monumented cross sections where we just, you know, we just know where we go across to do a cross section, and you know, we could describe how the bed changes. It clearly does a lot just from walking around out there.
Yeah, I have a bunch of questions and things I'm excited about, but I'm actually just talk to Jamie later because it's probably not worth keeping everybody else held over, and that way we can let Kathryn go also.
Sounds good. Why don't we do that? Casey.
Hi.
Hi. Do you want me to run the slideshow, or?
I mean, I could probably try to do it.
Sure. Okay.
What?
I'm gonna make you presenter now. We see your screen. Looks good.
You see a full slide, or do you see like something that's not quite correct?
We see like the notes view with.
All right. Perfect. Okay. I will follow and use the PDF that I made, and let's see if this works.
That should work.
Does that look okay?
Yep.
Okay. All right. Well, thank you, Jamie. Very interesting work. So today I'm going to talk about the second paper that I'm working on, and hope to get back out to co-authors soon. But so it's essentially just a summary of that paper, and then there are a couple points, 2 points throughout the presentation where I sort of have like any thoughts or any recommendations. So we can even stop then or wait until the end. All right. So essentially, So this paper, I really focused on quantifying the yields of particulate organic carbon, or POC, from the Luquillo Critical Zone Observatory, focusing specifically in Mamaeus and Icacos. And then, but beyond that, we're trying to think about the role of hot moments, and as I'll get through with this talk, and I know I've spoken about this several times, so just bear with, but I'll look at the role of extreme storms during this period.
You still there, Casey? I can't hear you.
Yeah, I can't hear her either.
Yeah, me neither.
I just chat messaged her saying we can't hear her. Casey's going to join another way, and I'm going to run the slideshow for her. Do you see my screen now with Casey's first slide?
Yes.
Great.
Yep.
I think Casey's just going to call in, so I'm sure she'll say hello when she gets back on. Oh, all right. Just a second.
Hello?
Hello, Casey.
Okay. Sorry about that. Can everyone hear me okay?
Yep.
Yep.
Okay.
Yep.
Sorry, I have an old laptop from my start of my PhD. I think it's probably time to upgrade. Okay. So, all right. So, great. We're on the right slide. So just briefly, I'll just quickly go over what particulate organic carbon is. It's generally 1 to 8% of river suspended sediment, and it can contain two different types of sources. One would be biospheric, and which is the only type we really have in Luquillo, which consists of soil, vegetation, and intermaterial. And then we can have petrogenic sources of organic carbon. So it's just like ancient carbon from mudstones. Okay, so next slide, please. All right, so why is all of this important? And so essentially, I can't really point to it, but if you can kind of see the river where it says export of organic carbon at 0.03, essentially what happens is that you have photosynthesis and respiration, and sometimes you have, and obviously you have on-site deposition, for example, with soil, but essentially in terms of the long-term carbon cycle, if you really want to trap atmospheric CO2, one of the best methods is actually to remove it from the landscape via rivers, for example, and then deposit it in long-term depositional areas such as oceans or lakes. And so this transport is really the focus of my work here. Okay, next slide. All right, so just, everyone's familiar with our study area, and for this work I focus specifically on Rio Mamaeus and Rio Acacos because they have the best sort of sample set of suspended sediment samples and also quantified discharge. All right, next. Okay, so what did I do? Now, I guess just as an overview, this is sort of a summary of my postdoc on this work, and this was the main point of coming. And so, one thing that I did was locate a whole bunch of suspended sediment samples from either our collections, and also using USGS samples. So there's a lot of suspended sediment samples, as you can see, over 4,000 between the two rivers. And the collection span from, the late, 18, sorry, 18, that'd be great, 1989 to 2015. And we have, really huge concentration ranges, so it's pretty amazing. And we have, and as well, a really large hydrograph range, with some samples actually even collected during hurricanes. And so in these photos, or in these graphics below, which a lot of you have seen multiple times, but what I've got are the suspended sediment samples are sort of the gray background, and then over top of those are the colored samples, or the ones that I was able to run for POM. And you can just see just what an amazing spread that we have for the area in terms of runoff, increment increases, and also with suspended sediment increases. Okay, so next slide. Okie doke. So over my time, I was able to analyze just over 400 suspended sediment samples on the elemental analyzer, and these are just the basic results. So you can see runoff compared to concentrations of particulate nitrogen, so PN, and then the POC. So that's just for visual. Okay, next slide. Okay, so getting down to some of the results, or what did we find? Essentially, first of all, one of the main things that was really important that we found was that the POM percentage, so the percentage of particulate organic matter in suspended sediment remained relatively constant with an increasing suspended load, which is quite interesting, and I can get into that further if anyone has any further questions later. But I'll just pass that on for right now. One thing that you can note as well, especially if you look at the graphs below, less than 1 milligram per liter of suspended sediment. There's something that's quite interesting that happens at Rio Mamaeus, and that's just like you have this huge increase of your carbon and nitrogen percentage. And what we were able to show in the paper that the storm paper that we recently published in WRR was that you actually have a large in-stream source at Rio Mamaeus that you don't really have at Rio Acacos. And these are just at really low discharges, but you have to kind of deal with these situations differently. But essentially, what we saw was that beyond this very low flow was that the contributions of POM remained relatively consistent. And then the numbers here, in case you're interested, are, it just shows what the percent carbon and nitrogen was for over this time period. So you can see, for people that don't know too much about POC, for example, in rivers, we have like 4.5% in the Akakos and 5.8% as a mean. So, and generally in world rivers we see about 2%. So that's quite interesting. And I'll get there's another slide later that I will talk about, but I would be interested to hear what they think about this high carbon content or organic content. Okay, so next slide.
Casey or anyone else, I'm sure it varies across the hill slope landscape, but what's a good representative number for carbon content of the hill slope surface soil? Do you know?
Maybe someone else can. I know I have a. I definitely analyzed some samples and have it in the paper, but I can't think of offhand. Does anyone else know offhand?
Wendy's our expert, but it's about a couple percent typically. Sometimes in the riparian zone it can be up as high as 7 or 8%, but typically it's a couple percent, and then at depth it gets much, much lower to tenths of a percent. That's what I'm thinking.
Yeah, I agree with that. This is Wendy.
Great, that's a really good point. I'll look into that, because that would be good evidence to think, to compare to why we could be seeing this. Although, if you think, I know in my PhD, for example, where, we had soils that were up to like even 44, they're organic soils, but like sometimes it was really, really high percent carbon, but then in the rivers they're really quite low. So I think that this is something that is in order to submit the paper, I need to kind of sort out. So thank you very much for that suggestion. All right, and I'll look into that. Okay, right. So are we're on the next slide, Miguel? No, can you go back up? Where are we? And then one more. Okay. Yeah, okay, so yeah, right, you're on the right one. Okay, so next. All right, yeah. So, yeah, I think that's a really good idea about thinking about soil carbon content. In terms of, why we could have, you could also take it on the other sort of viewpoint, which would be like you could look at it through the suspended sediment. Why could that maybe be reduced for some reason? And all views welcome, but I was thinking that if we have high chemical weathering in some regions, if the material is actually just being dissolved and removed, maybe that could be a potential contribution difference. And then also maybe just I know I said low transportability of the quartz, and then we just saw in the last presentation that we have, huge flushes of this material coming through. So, but in the sense, what I meant was that like we relatively have sometimes larger pieces in the Akakos, for example. So that sort of fine suspended sediment that's like mineral, rock derived is kind of different, and this might be, for various reasons. But any thoughts on that would be welcome. But those were two of the thoughts that I thought of. It could be a combination of the system working.
Well,
yeah.
Well, the other thing we have to keep in mind, because not everybody thinks about sediments and carbon in sediments as much as some of us do, that the load as we define it is, it can also include chunks of leaves from the stream channel, and then also material that's wouldn't be called soil, but the litter layer, the humus layer in the forest, of course, can be highly organic. So there's an interesting question about the extent to which our soils somehow reflect a sort of low, there's relatively low accumulation of organic matter in the upper horizons compared to a lot of places, and there's no like deep forest flora like we have in New Hampshire. Yet at the same time, the underlying mineral soil actually has, because of all the clay and whatever, has a lot of carbon that's associated with that mineral soil. It's kind of right on the surface in a lot of cases. So it's an interesting, obviously what's in the stream reflects watershed and stream processes, and so it's just a perspective to keep in mind.
Hello?
This is Wendy. We were just looking at some data yesterday from my lab where we've been playing with trying to desorb carbon from soils using redox fluctuations and pH and changes in pH. And what we're finding is that the DOC flux from soil is really hard to shift in the laboratory.
Okay.
And so it's almost as if carbon comes in and carbon goes out, but that the soils either they maintain there's enough carbon coming in that they maintain their carbon stock really well, so that it's coming on and coming off in equilibrium or some sort of steady state, and that's probably the case because the carbon's relatively young from a C14 perspective.
Mm.
But it seems as if it's not, it's not accumulating, and it's hard to get it to decrease. So I'm wondering how coupled they really are.
Yeah, one thing that I didn't show because I just thought it was a bit much for this talk, but one thing I do want to mention, and it's part of this paper, is we actually also have LOI data for a lot of the samples, and what we find is that there's an equation. So essentially, loss on ignition is carbon plus the water loss from clays. But Bob Stallard worked out this equation, and there are some figures which I don't have here, but essentially we do show essentially the LOI decreases with an increase of discharge, but we actually show that POM stays constant. So that would make sense that the clays would reduce as you're getting more of these large particles, quartz and things like this coming through the river, but it also sort of suggests maybe like what Bill was saying, that in terms of sources and where the carbon's coming from, that would be an interesting point, like what carbon would be associated with the clays, and is that even important at high discharges? For example, so more like from litter or organic soil, why is it staying, a consistent percentage when you have the clays, and I would imagine that things associated with those clays dropping off with an increase of discharge. So that's just another point I wanted to make there.
And I just would weigh in on the LOI measurements, and this may be different between what you guys do in stream channels and what we do on soils, but we did because people historically a long time ago used LOI on soils more frequently than they do now. Now we use carbon nitrogen analyzers, elemental analyzers that combust the organic matter and measure the CO2 directly. And so I had a student do a project in my lab where we tried to correlate from Luquillo, from Bislay, a lot of samples that had been measured for LOI a long time ago. We then measured the carbon content of those using an EA, and we found no correlation.
And so that's probably because of the water loss of the clay.
Absolutely. So the water loss is variable enough that it swamps the carbon signal, and so if LOI is being used as an index of carbon content or organic matter content, we also did some, if I remember correctly, we did some Walkley Black, which is a chemical assay chemical oxidation assay that gets at organic matter content, not just carbon. And that also, we did that on a subset of soils. That also did not correlate. So I can hunt that up. That was actually, I think, a project that Yit Tay did when he first came to my lab many years ago. So just a note that LOI data can be misleading if you're trying to relate it to carbon content.
Well, I think that's what Kathryn was saying, aren't you, Kathryn? Is that the LOI and the carbon content weren't related.
I think we lost Kathryn.
So, Kathryn, or maybe Miguel, if you're handling the slides, I would really like to just go back to that graph that showed the Mamaeus. Yeah, right, just right there. No, just the other one right there. And I guess I was going to ask Kathryn a more detailed question, but she might not be able to answer it.
I'm messaging
Kathryn,
her.
are you back?
See if she's still connected.
Sorry, I muted myself.
You muted yourself. Okay.
I'm sorry. Because I'm talking on the phone and it pressed up against the thing. I was wondering why I couldn't interject. Okay. Sorry. I also have something to say about what Wendy was saying, but should I deal with that first or?
Sure.
Okay. So we do realize that about the issue with the LOI, and this is what we've done. This paper, Bob, and we have corrected that issue with LOI, and the only time that we use LOI as a guide is at really high discharges where we don't have samples, and it's just so we don't overestimate the role of the POM. So it's like it sets the limit, because as you'll see, or have we gotten to it? Essentially, once you're at high discharges, high suspended sediment concentrations, you have really high POM concentrations. So it's just to set a limit so we don't overestimate. So that's what we've done. It's just as a tool, and we have Bob thought of this very good equation that we have in the methods, but we do realize that the LOI is not directly, it's not so easy to understand what's going on. We just use it as like in those specific cases, not to overestimate the POM. Does that sound good? And I would be very interested in seeing the work that you've done, and maybe we can cite it in the paper.
Sure.
Hey, before we ask the question from Aaron, Kathryn, you should just be aware, you may not be aware, that there are about 5 or 6 years of the full LTER set, which is heavily weighted towards the low flow, where the Forest Service did do LOI on every filter. And so those should also, at low flow, you would expect then a big loss. And so it may be a lot more of the low flow samples, I'm saying, where with little clay, the water hydration issue is minimized relatively. And thus the LOI may be a more useful. I mean, those are high percents you have on those few samples. So it might be worth looking at the LOIs that we have from those 5 or 6 years, start in the early 2000s, and if you can't find the data online.
No, we've definitely. I'm sorry. I mean, we've definitely done that, and it's in the paper.
Oh, okay. Okay,
yeah. I'm not sure who's talking right now, but we've definitely done that in the paper, and it was a huge consideration. Sheila can attest to that. So we have that all considered there. But that plot that you're seeing is literally just my results from the elemental analyzer. It's nothing to do with LOI. Should we just continue? Maybe I'm not actually sure of the time.
Oh yeah, you have more slides. Okay.
Yeah.
Okay.
Yeah,
sorry, it looked like it was a concluding thing, so we were kind of, I think, all ramping up for questions. So.
No, it's just like I have questions.
Yeah,
so I guess we'll just have to. I see the time now. Okay. All right. So let's. But thank you very much. Okay. So next. Oh. Okay. Sorry. Yeah. So as I said, Bob Staller ran low test for many years, and we worked on this for over, Sheila and everything worked on this for over a year or two. So let's go into the results, I think. Next slide. Okay, so these are the results for the runoff, suspended sediment, POC, and the PN. We can talk about anything about this, but generally what we know is true is that the Akakos has a very important role. I think we could just carry on, because I think we're supposed to finish at 10 after, right? Or is it?
We could go as long as people want, no longer than 1:30, but I actually have to leave in about 10 minutes to go over to NSF.
Okay, well, all right, well, let's shoot for Bill's aim there. Okay, so let's carry on, and if anyone has any questions, we can go on afterwards. Okay, so next. All right, so can you see the whole slide here? I guess maybe so I can't. Okay, there we go. Okay, so now if we look at a global comparison of POC compared to suspended sediment, I pose another question, but we will come back to this at the end. We've got global rivers are the black and gray lines, with mountain rivers being the black ones, or circles, sorry, and then ours are the Akakos and Mamaeus are here just sort of above the sort of global trend. But I want to note, and this is sort of the direction where we're going with the paper, is that Capostete, which is nearby, also has this elevated carbon content compared to the suspended sediment. And the question is, why might this be? But we've already sort of established that. So let's just continue on, and then we can talk about that later. All right, so the main thing, and this has been published recently, is the role of climate as a sort of a terrestrial biosphere sort of driver of the removal of the POC. And so what you can see in this plot is now we're looking at runoff compared to POC, and we've got Bob Hilton's sort of collection of mountain rivers here as black, and then we've got the Capostete as the green, and then our samples are the purple and red, and you can really see as we would expect, higher runoff, we have higher POC. So higher yields with higher runoff have higher POC. Let's continue on. Okay, so then we're thinking about hot moments. I wanted to really address the role of climate specifically. So so Martha Scholl and Sheila Murphy had a paper, sorry I didn't reference it, but essentially they were able to isolate rainfall events affecting Luquillo, specifically Rio Akakos, over an 18-year period. Okay, continue. Okay, so essentially what I wanted to do was get these clip out the largest storms, and then ask Bob Fowler to extract what was the carbon and the suspended sediment and the water, what actually came out during these individual storms. And what you can see is actually quite interesting. So on the x-axis we have storm rank. So from like the largest storm would be around 0, like it would be 1, and then the smallest of the large storms, because these are only large storms, about I think it's above 80 millimeters of rainfall in a specific event. So there's 125 storms that fell into this category over the 18 years. And what we can see is really quite interesting. In terms of cumulative frequency, or 50%, what actually happened there? Okay, well, in terms of POM and suspended sediment, actually, it only takes a couple storms, like less than 10, within that whole 18-year period to mobilize 50% of that load. Whereas runoff and rainfall is much less, specifically rainfall. So you can, kind of interesting result there. So, yeah, let's go to the next one. I think there's one more. Okay, okay. So, and then we're all interested in the role of cyclones. But really what ends up happening, and sorry that this is a kind of a lot to look at here, well, essentially over this time period, we had about 10 cyclonic events. Now, this was after Hurricane Hugo, just as a note. But what you can see was that actually not much of the annual runoff occurred during these cyclones, but about a quarter of all COM was mobilized during those time periods, and it kind of represents on average about 6 days of a year if you just average the whole 18 years. And then there's some detail there, but the point I really want to make with this is the role actually of sort of unnamed storm events, you know, because if we're seeing that large storms over 80 millimeters of rain, if we can see in this table in the upper right, we have in terms of POC, not DOC, I just have there as an example, but it's not actually in the paper. But if you look at suspended sediment, POC, and PN during storms, you know, you're getting upwards, you know, 60% or greater during what we call storms. But if you just look at cyclones, it drops dramatically. And obviously this has to do with the frequency of cyclone events during a year. But it also just goes to show what are the important role that unnamed systems, I think such as cold fronts, can actually play on the Luquillo Mountains in terms of mobilizing carbon. Okay, and sediment. And you know, for example, I'd be interested, Jamie, to know what types of storms yours were that you got over this recent Easter break. Okay, and then this is my final slide, and we can just take questions, but that's sort of just a summary of everything. And that's finished. Everyone here okay?
Yep.
Yeah, I'm going to have to go, guys. I'll be late for my meeting with the program officers. Thanks. It's very cool, Kathryn. I like the storm analysis. It's come further than what I saw before. It's very cool.
Great, yeah. And I'll send you an email with some stuff. Okay.
All right. Yeah. I look forward to it. Yep. Bye-bye.
Bye.
Bye.
Are there any
Kathryn,
questions? Sorry, I was a bit rushed at the end. Yes?
This is Jamie. I have a question. So on your slide where you showed that the percentage of carbon in the suspended sediment was fairly constant, it was striking the way it really stayed. That line is pretty horizontal over a huge range of discharge, but there's quite a lot of variability. Do you think that is from hysteresis, or any explanation for, it's like a 3 to 5-fold variability it looked like?
But like in terms of like if it ranges from say 1 to 12% or something?
Yeah, it looked like the
you
meat
mean
of the
like
range
that?
was maybe 3 to 8%.
Yeah, 3 to 8. Yeah, so I don't know, Miguel, if you want to go back to that slide. I realize, did I show it? I don't think I have it in here, but essentially that is definitely a consideration, but considering you know, at least for the yields paper, this is what we have to do. You just kind of have to summarize often. But, you know, just as we showed in our paper, we definitely see that sort of these hysteresis loops where, you know, quite likely you get a sample, you know, like what you showed. You have high turbidity, you have high suspended sediment, and you have high carbon concentrations. You know, and within there's going to be a range all the time depending, you know, so there's different sort of issues that are going on, but I think that's definitely something to think about. But that's just how we did it for this paper, was to just take an average in order to get the overall sort of input. But definitely, for example, when we were at the conference, at the Chapman conference, one of the things that I wanted to do or suggested to do would be to look at what discharge, you know, was it on the rising limb or the falling limb compared to the percent carbon or nitrogen that we actually measured. And that was something I suggested to do for one of the Chapman papers when we're thinking about general characteristics of rivers during storm events. But I have not looked at that specifically. But definitely a very interesting question.
It would be cool to see that plot with the rising limb samples in one color and the falling limb in the other.
Yeah, as a percentage, because you know, and then of course not as a log plot. Like, because you know, when you log something and it's like a concentration versus concentration, actually for suspended sediment carbon, it fits on like a 1-to-1 line, and so this is our rationale to just use a consistent percentage. Because in the longs, you know, when you're thinking about concentrations, the percentage within there isn't that important in the overall yield of the POC or nitrogen. It's the concentration to suspended sediment concentration. But yeah, I'll definitely write that down and look at that for that one paper that we haven't started yet. Anyway, okay. Any other questions? No?
Thanks.
No?
Thanks.
Okay.
Just a reminder to both of our presenters, I did record this. Is it okay if I put it on YouTube?
Sure.
Yeah.
Okay.
Yeah, I'm sorry about the phone.
No problem. It worked out.
Okay, well, thanks everyone for listening.
Thank you guys.
Bye.
Bye. Take care.
Bye.